Tonight, NASA has confirmed that after 36 years in space, Voyager 1 has left the solar system as we know it. That's farther than any man-made object has gone before, into interstellar space about 11.5 billion miles away.
7 minutes ago, Voyager 1 sent back a set of readings that don't fit any current model of interstellar space.
We knew we were on a journey of discovery when we launched the Voyager spacecraft, but we had no idea how much there was to discover.
The instruments are working. The data is consistent. Every system is behaving exactly as it should. The only problem is what it's measuring, because the environment it's describing isn't supposed to look like this. The machine that outlived its design. By the time Voyager 1 left the inner solar system, it had already done everything it was built to do. It had flown past Jupiter, captured detailed images of Saturn, and sent back data that redefined what scientists understood about the outer planets. The mission was never meant to last decades. It was designed for a short window of exploration, a few critical flybys, and then a slow fade into silence. But that didn't happen. Instead of shutting down, Voyager 1 kept going. Its power source, a radioisotope generator fueled by decaying plutonium, continued producing just enough energy to keep a handful of instruments alive. Over time, engineers began turning systems off one by one, not because they failed, but to conserve what little power remained. Cameras were shut down. Non-essential instruments were disabled. What was left was the bare minimum needed to keep the spacecraft communicating. And yet, it kept transmitting. Decade after decade, signals continued to arrive. Weak, delayed, but consistent. Each transmission carried data from farther out than anything humanity had ever measured directly. Voyager 1 wasn't just leaving the solar system. It was moving into a region no spacecraft had ever entered before. That alone would have been enough to make it one of the most important missions in history. But the further it traveled, the more its role began to change. It was no longer just exploring planets. It was approaching a boundary. For years, scientists had defined the outer edge of the solar system based on the reach of the sun's influence. The solar wind, a stream of charged particles flowing outward from the sun, creates a kind of bubble around the solar system known as the heliosphere. Inside that bubble, the sun's magnetic field dominates. Outside of it, the environment is shaped by the interstellar medium, the matter and energy that exist between stars. The boundary between these two regions is called the heliopause, and Voyager 1 was heading straight toward it. This transition was not expected to be gradual or ambiguous. The models were clear. As the spacecraft approached the heliopause, the solar wind would weaken, the density of interstellar particles would increase, and most importantly, the direction of the magnetic field should change, shifting from one dominated by the sun to one aligned with the galaxy. It was supposed to be obvious, a clean break, a measurable crossing from one region of space into another. Voyager 1 was carrying the instruments needed to detect that transition. Even in its reduced state, it could still measure magnetic fields, plasma waves, and charged particles. It was, in effect, a sensor moving steadily toward a line scientists believed they understood. And as it got closer, the data began to shift. Solar particles decreased. Cosmic radiation increased. The density of plasma changed in ways that matched predictions. Everything pointed toward one conclusion. Voyager 1 was reaching the edge. But there was one problem. The closer it got to that boundary, the more important a single measurement became: the direction of the magnetic field. Because that was the one signal that could confirm without ambiguity that the spacecraft had left the sun's influence behind. It was the detail that would separate theory from observation, expectation from reality. And when Voyager 1 finally reached that point, that signal didn't change the way it was supposed to. The boundary that didn't change. In August 2012, Voyager 1 reached the point scientists had been waiting for, the moment it crossed the heliopause, the outer boundary of the sun's influence. Based on decades of models, this transition was expected to be one of the clearest events ever recorded in space exploration. The predictions were specific. As Voyager approached the boundary, the solar wind, streams of charged particles flowing outward from the sun, would drop sharply. At the same time, cosmic rays from outside the solar system would increase. And most importantly, the magnetic field should shift direction, changing from a solar alignment to one controlled by the galaxy. 3 signals: clear, measurable, and consistent. So when the data started coming in, 2 of those signals appeared exactly as expected. The solar wind weakened, cosmic radiation increased. Everything suggested that Voyager had reached the edge of the heliosphere. But the 3rd signal, the most important one, didn't change. The magnetic field stayed aligned in almost the same direction. That shouldn't have happened. Crossing into interstellar space was supposed to feel like stepping into a different environment. The magnetic field on the other side should have a different orientation, shaped by forces beyond the solar system. Instead, it was as if Voyager had crossed the boundary and found the same structure continuing, like walking through a door and seeing the same room. At first, scientists hesitated. The data was clear, but the interpretation wasn't. Had Voyager actually crossed the heliopause? Or was it still inside a region influenced by the sun in ways that weren't fully understood? The measurements didn't give a simple answer. They created a contradiction. Because if Voyager was still inside the heliosphere, then the increase in cosmic radiation didn't make sense. But if it had left, then the unchanged magnetic field didn't make sense either. The boundary was supposed to resolve that uncertainty. Instead, it created it. Further analysis confirmed that the plasma density had increased significantly, matching what scientists expected from interstellar space. This supported the idea that Voyager had indeed crossed into a new region. But the magnetic field continued to behave as though it was still connected to the sun. That left only one possibility. The boundary wasn't what scientists thought it was. Instead of being a sharp edge separating 2 distinct regions, the heliopause appeared to be more complex, a transition zone where properties from both environments overlapped. The sun's magnetic influence didn't simply stop, it extended outward, interacting with the interstellar medium in ways that blurred the distinction between inside and outside. This changed the meaning of the crossing. Voyager hadn't moved from one clearly defined region into another. It had entered a space where the rules were less clear, a space where the sun's influence and the galaxy's influence existed at the same time. And that raised a deeper issue, because if the boundary itself was not clean, then every measurement taken within it became harder to interpret. The data was no longer describing 2 separate systems. It was describing an interaction between them. And interactions are harder to model, harder to predict, and harder to fully understand. Which meant the anomaly wasn't just the magnetic field, it was the assumption behind it. Because everything about that crossing had been based on the idea that the edge of the solar system could be clearly defined. But Voyager's data suggested otherwise. It suggested that the edge wasn't a line, it was a region. And the moment scientists accepted that, a new question replaced the old one. Not whether Voyager had crossed the boundary, but what kind of boundary it had actually crossed into. The signal that didn't match. After the 2012 crossing, Voyager 1 didn't stop providing data. It kept moving outward, deeper into what was now considered interstellar space. And with each passing year, its measurements were expected to stabilize. Once beyond the heliopause, the environment should become more uniform, shaped less by the sun and more by the broader structure of the galaxy. That was the expectation. But the data didn't settle the way it should have. One of the key instruments still active on Voyager 1 was its plasma wave system, which detects oscillations in charged particles. These plasma waves are important because they reveal the density and behavior of the medium the spacecraft is traveling through. In interstellar space, scientists expected relatively steady readings, with occasional disturbances caused by distant cosmic events like supernova shockwaves. And at first, that's what the data seemed to show. Voyager detected bursts of plasma waves that allowed scientists to measure the density of the interstellar medium with surprising precision. These readings confirmed that the spacecraft had indeed entered a region denser than the heliosphere, reinforcing the conclusion that it had crossed into interstellar space. But over time, the pattern of those signals began to change in ways that didn't fully match the models. Some of the variations were tied to known events, like shockwaves propagating through space from distant stellar explosions, but others appeared without a clear source. The density would increase, then stabilize, then shift again. These changes weren't extreme, but they were consistent enough to raise questions. Because interstellar space, at least in theory, should not behave like a highly dynamic system at that scale. It is vast, diffuse, and relatively uniform compared to planetary environments. Small variations are expected, but not persistent fluctuations without clear causes. Voyager was detecting the structure. At the same time, its cosmic ray instruments were recording changes in high-energy particle intensity. These particles, originating from outside the solar system, should follow predictable patterns once the shielding effect of the heliosphere is removed. But even these readings showed variations that didn't align perfectly with expectations. What made this more significant was how these different systems began to overlap. Plasma density changes, cosmic ray fluctuations, and magnetic field behavior were all showing small inconsistencies at the same time. The environment Voyager had entered was not as simple as the models suggested. It was structured, and that brought the focus back to the boundary. If the heliopause was not a clean separation, and if the region beyond it was not fully uniform, then Voyager wasn't moving from one stable system into another. It was moving through layers, which meant the fluctuations in its data weren't necessarily errors or anomalies. They could be measurements of something more complex than expected, something that hadn't been fully accounted for in the original models. And that shifted the interpretation again, because now the question wasn't just about the boundary itself, it was about the nature of the space beyond it. The forces we didn't factor in. By this point, the pattern was hard to ignore. Voyager 1 had crossed the heliopause, but the transition wasn't clean, and the space beyond it wasn't uniform. Plasma densities shifted. Magnetic fields didn't fully realign. Particle behavior overlapped across regions that were supposed to be separate. At first, these were treated as anomalies, but over time a different interpretation began to take shape. The problem might not be the data, it might be the model. For decades, the heliosphere had been described as a kind of protective bubble around the solar system, formed by the outward pressure of the solar wind pushing against the interstellar medium. The boundary, the heliopause, was thought to be the point where those two forces balanced. But real environments are rarely that simple. When scientists started re-examining Voyager's data in detail, they began considering the possibility that the heliosphere isn't a smooth, symmetrical structure. Instead, it may be distorted, stretched, and shaped by external forces in ways that weren't fully accounted for. One of the most important of those forces is the interstellar magnetic field. Unlike the Sun's magnetic field, which radiates outward, the interstellar field exists on a much larger scale, influenced by the movement of the galaxy itself. As the solar system travels through this medium, the interstellar magnetic field doesn't simply stop at the heliopause, it interacts with it. This interaction creates a phenomenon known as magnetic draping, where interstellar magnetic field lines wrap around the heliosphere instead of passing cleanly through it. Instead of a sharp boundary, you get a layered region where the solar and interstellar fields overlap and influence each other. That changes everything. Because if the magnetic field outside the heliopause is being bent and aligned along the surface of the heliosphere, then Voyager crossing that boundary wouldn't immediately detect a new direction. It would detect continuity, which is exactly what the data showed. The magnetic field didn't change abruptly because it wasn't supposed to. It was being shaped by the interaction between two systems at once. But that still doesn't explain the fluctuations, because draping alone would create a smoother transition, not the layered variations Voyager detected. That led scientists to consider additional factors, including turbulence at the boundary. Instead of being stable, the heliopause may be constantly shifting, with regions of mixing where particles from the solar wind and interstellar medium exchange energy. Think of it less like a wall and more like a current. That kind of environment would naturally produce the kinds of variations Voyager recorded. Plasma densities would fluctuate, particle distributions would shift, magnetic fields would appear consistent in some areas and slightly altered in others. The signals Voyager sends take over 20 hours to reach Earth. What scientists are analyzing isn't real-time data, it's a delayed snapshot of conditions that may already have changed by the time they're observed. That makes it even harder to reconstruct a stable picture of the environment. All of this points toward a single conclusion. The region around the heliopause is not a boundary in the traditional sense. It's an interaction zone, a place where forces overlap, compete and reshape each other continuously. And Voyager didn't just cross it, it's still moving through it, which means the fluctuations in its data aren't just remnants of a transition. They may be ongoing measurements of a system we don't fully understand yet. And that leads to a deeper implication. Because if the outer edge of our solar system is this complex, then the idea of a clear separation between inside and outside may not apply at all. And that changes how we think about where the solar system actually ends. Where the solar system actually ends. By the time Voyager 1 crossed what scientists call the heliopause, it should have marked a clear milestone. But the data never fully supported that idea. Because if the heliopause is not a clean boundary, if it is instead a region where solar and interstellar forces overlap, then the concept of an edge becomes harder to define. Voyager didn't move from one side to another. It moved into a zone where both environments still exist at the same time. Inside the heliosphere, the Sun dominates. Outside of it, the galaxy does. That distinction is what allows scientists to define where the solar system ends and interstellar space begins. But Voyager's data suggests that distinction may not be absolute. Instead, the solar system may extend farther than we thought, not as a defined structure, but as a diminishing influence. The Sun's magnetic field, its particles, and its energy don't just stop at a line. They weaken, interact, and blend into the surrounding medium, which means there may not be a single point where the solar system ends, only a region where it gradually fades. And that has real consequences for how we interpret Voyager's position, because while it is technically in interstellar space, it is still detecting effects that are tied to the Sun. The magnetic field alignment, the particle behavior, and the plasma fluctuations all suggest that the solar system's influence hasn't fully disappeared. This also explains why Voyager's data doesn't fully match interstellar models. Those models assume a cleaner environment, one where local influences are minimal. But Voyager is measuring a space where those influences are still interacting. A space that is not fully one thing or the other. That means every reading Voyager sends back is part of a larger transition, not a fixed state. And transitions are harder to interpret than stable systems. They contain overlapping signals, shifting conditions, and interactions that don't settle into predictable patterns, which is exactly what Voyager has been detecting. And that leads to a more precise way of understanding what Voyager has actually done. It didn't reach the edge of the solar system. It reached the limit of how clearly we can define that edge. Because if the boundary itself is not fixed, then the idea of crossing it becomes less meaningful. Voyager didn't move from one known region into another. It moved into something that is still being defined. If the solar system doesn't end where we thought it did, then what exactly have we been measuring all this time? What Voyager is actually showing us? After everything Voyager 1 has recorded, the biggest shift isn't in the data itself, it's in how that data is being interpreted. For decades, space beyond the solar system was treated as something simple. A vast, mostly empty region where particles drifted, magnetic fields stretched across long distances, and changes happened slowly and predictably. The heliopause was supposed to mark the transition into that simplicity. But Voyager's measurements don't support that version of space. They describe something layered, structured in a way that isn't immediately obvious. Magnetic fields that don't fully separate, particle densities that don't stabilize, regions that don't behave as cleanly as the models predicted. And none of this points to something external or unknown. It points to something more fundamental. The models were simplified. They treated space as if it could be divided into distinct zones with clear rules. But Voyager's data suggests those rules overlap. The solar system doesn't end at a fixed point. Interstellar space doesn't begin in isolation. The two interact continuously, shaping each other across a region rather than a boundary. Which means what Voyager is showing us isn't an anomaly. It's a limitation of the assumptions used to understand what it's measuring. Voyager didn't reach a place where physics breaks down. It reached a place where our descriptions of physics become less precise. The fluctuations in plasma, the alignment of magnetic fields, the overlapping signals, none of these are errors. They are measurements of a system that operates across scales and interactions that are harder to isolate than previously thought. We didn't send Voyager far enough to reach something completely new. We sent it just far enough to realize how much of what we thought we understood still needs to be redefined.